So, part 7 of Advanced Engineering Mathematics Practice Final Exam, number 19 here. We want to evaluate the following: closed integral over C, closed contour integral over C here. Z cubed plus 2 over quantity Z minus 1 squared, Z plus 2 dz, where C is the circle, modulus of Z equals 3. Using residue theory. So, contour integration problem. So again, we're given the following integral, the closed contour integral over C, numerator Z cubed plus 2 over denominator, that quantity Z minus 1 squared Z plus 2 dz, where the modulus of Z equals 3. So modulus of Z equals 3. The poles are going to be at Z equals 1 and Z equals negative 2. And both lie inside that modulus of Z equals 3. So at Z equals 1, there's a second order pole. So the residue is here, F at 1 equals this d dz of Z cubed plus 2 over Z plus 2, Z equals 1. So d dz of Z cubed plus 2 over Z plus 2, using the quotient rule here. Numerator 3z squared times the quantity Z plus 2 minus quantity Z cubed plus 2 over quantity Z plus 2 squared. And at Z equals 1, our residue here of F at 1, that's going to equal 3 times 1 times 3 minus 3 over 9. 6 divided by 9 equals 2/3. So from here at Z equals negative 2, the residue of F at negative 2 equals that limit as Z approaches negative 2 of Z plus 2 times that Z cubed plus 2 over quantity Z minus 1 squared times the quantity Z plus 2. So the residue F at negative 2, that's negative 2 cubed. Negative 2, that quantity cubed, plus 2 divided by the quantity negative 2 minus 1 squared. So that's negative 8 plus 2 over 9. Negative 6 divided by 9, that gives us negative 2/3. So taking the residues and adding them, the sum of the residues, that's 2/3 plus a negative 2/3, which is 2/3 minus 2/3, that equals 0. So therefore we wind up with 0. Okay, so I'm moving along now to number 20. Number 20, we have f of Z equals sine of Z over Z squared times the quantity Z minus I. Determine all singularities. Order of each singularity, Laurent series about Z equals 0, and the residue at each pole. Okay, so Laurent expansion and singularities. Okay, so for this, we have the following. F of Z equals sine Z over Z squared times the quantity Z minus I. So the possible singularities are at Z equals 0, Z equals I. And at Z equals 0, sine of Z is asymptotic to Z. So f of Z is asymptotic to Z over Z squared times the quantity Z minus I. And that equals 1 over Z times Z minus I. So Z equals 0 is a simple pole. At Z equals I, the denominator has a simple factor Z minus I. And sine of I cannot equal 0. So Z minus I is also a simple pole. Residue at Z equals 0, or residue of F at 0, that equals a limit. As Z approaches 0 of Z, sine Z over Z squared times the quantity Z minus I. So the limit as Z approaches 0, sine Z over Z times the quantity Z minus I. And since that's sine Z over Z, that's going to approach 1. The residue of F at 0, that's 1 over negative I. Simplifying that, that becomes I. So the residue at Z equals I is going to be residue F at I equals a limit as Z approaches I of Z minus I, sine of Z over Z squared times Z minus I. And that's going to equal sine I over I squared. And since sine I equals I, hyperbolic sine 1, I squared is negative 1, the residue of F at I equals negative I, hyperbolic sine of 1. So for the Laurent series about Z equals 0, sine of Z equals Z minus Z cubed plus Z to the 5th over 120 minus, and on and on and on. And then sine z over z squared equals 1 over z minus z over 6 plus z cubed over 120 minus, and the pattern goes on and on and on. Also, 1 over z minus 1 equals I over 1 plus iz. That equals the following here. I times the quantity 1 minus iz minus z squared plus iz cubed plus a dot dot dot, where the modulus of z is less than 1. And for here, f of z equals the quantity 1 over z minus, that's z over 6 plus z cubed over 120 minus dot 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 times I times the quantity 1 minus iz minus z squared plus iz cubed plus dot dot dot. And the principal part starts as f of z equals I over z plus 1 minus iz plus dot dot dot. So the residue at z equals 0 is I. Okay. And now number 21, we want to consider the transformation here for w equals 2i. I'm sorry, let me start this from the beginning. Consider the transformation w equals z minus 2i over z plus 2i. Determine the image in the w plane of A, the real axis, B, the upper half plane, and C, the circle. Modulus of z minus 2 equals 2. So conformal mapping problem, w equals z minus 2i over z plus 2i. So for part A, the image of the real axis, let z equal x, where x belongs to the real numbers. And then w equals x minus 2i over x plus 2i. Computing the modulus of w here, that equals modulus x minus 2i over modulus x plus 2i. That equals square root of x squared plus 4 over square root of x squared plus 4. That equals 1. So what we could say is the real axis maps to the unit circle. Modulus of w equals 1. Moving along to part B, the image of the upper half plane here. Test the point z equals I, which lies in the upper half plane. Then w equals I minus 2i over I plus 3i. That becomes negative I over 3i, which is negative 1/3. This lies inside the unit disk, so the upper half plane maps to modulus of w less than 1. Okay, and now for part C, we have the image here of modulus of z minus 2 equals 2. So we use the inverse transformation, starting with w equals z minus 2i over z plus 2i. We solve for z. W times the quantity z plus 2i equals z minus 2i. wz plus 2i. W equals z minus 2i. Z times the quantity w minus 1 equals negative 2i times the quantity 1 plus w. Z equals 2i times the quantity 1 plus w over 1 minus w. So we're going to let w equal u plus iv. The circle is the modulus of z minus 2 equals 2. Substituting the inverse map and simplifying gives u squared plus 2u plus v squared plus 4v plus 1 equals 0. From there, we complete the square. That's what the CTS is for. Complete the square. U plus 1 squared plus v plus 2 squared equals 4 after we do that. So the image is the circle. U plus 1 squared plus quantity v plus 2 squared equals 4. And in complex notation, modulus of w plus 1 plus 2i equals 2. So the transformed circle has a center negative 1 minus 2i and a radius of 2. Okay, so that's all for part 7. And that's the practice final exam. Thank you very much and have a great day.